So this is a session named Research Paper Trading Made Easy. So we are reading PC DeepNet, a GNSS positioning error minimization framework using permutation invariant deep neural network. First, just chunk it. So we need to understand what is GNSS. GNSS refers to Global Navigation Satellite. So what happens in this world? There are so many satellites out there in space. So these satellites are used for navigation. What is navigation? You want to go from one place to another. We use Google Maps. We use some other applications, some positioning applications, which will help us to reach that place. How is this possible? So basically, there are multiple satellites in the sky, in the space, which are helping. So if you are running, if you have observed, like if you are using Google Maps, then it is not that accurate. Why? Its position got changes to 10 meters, okay, 13 meters. It is not that accurate. So what this paper I could understand from the title is they are using some PC DeepNet, okay, and that will minimize the position error using something called permutation invariant, and they are using deep neural network. Okay, so first try to read this abstract. So global navigation satellite system face significant challenges in urban and suburban areas due to non-line of sight propagation, multipath effect, and low received power levels, resulting in highly non-linear, non-Gaussian measurement error distribution. So, global navigation satellite system, which is used for the navigation in the urban regions, and suburban means not that developed but kind of regions, and due to the non-line of sight, like why non-line of sight occurs, the signal coming from the sky just get get reflected from the buildings, and they are not in the straight line, so that is called non-line of sight. They are not directly reaching us, but they are reaching us by reflecting through the various objects in the surroundings, and that is called multipath effects. Okay, these are non-line of sight propagation, and those received power levels. If the signal got reflected from the buildings, it is obvious that there are some attenuation. So there is some low received power levels also, which result in highly non-linear, non-Gaussian measurement. Obviously, because the signal is not reaching us directly, then that will contain so much noise that could not be corrected easily. Okay, so in this light of this, conventional model-based positioning approaches, which rely on Gaussian error approximation, struggle to achieve precise localization under these conditions. So what is actual doing, what actual have been implemented, that something Gaussian error approximation equations are derived that are used to just correct those errors, but those errors are not Gaussian in nature. They are highly non Gaussian measurements. So how could we correct that with some equations that are not possible? These are highly non-linear. So uh, that could not be used. So to overcome these challenges, we put forth novel learning based framework. So now you could understand that if it is not like what deep neural network does is it is just like a math. Suppose I will show you. Okay, let me show you here. So so This is suppose right. This is some model, okay, and this model have to learn something. This okay, so this is something like we have found that on inputting 2 we are getting output 6, okay, on inputting 3 we are getting output 9. So what we'll do, we will feed all this to this model, and this model will learn. It will adjust some weights, okay, it will adjust its parameters, and after that the model learns something. The model derives. What it derives is is a mathematical equation. Mathematical equation. Okay. And these are highly complex mathematical equation. Okay. So these are the equations which is derived. Right. So this when these are the highly non like complex equation, highly complex equation, which could be used for Gaussian approximation. Okay, so in this slide convention, so they are using this to overcome challenge. We put null. Okay, so what they have named is PC DeepNet. It is a learning based framework that employs permutation invariant. Now, what is permutation invariant? So permutation invariant means that if order of something changes, then the output should not vary much or change. Like uh, like there is a equation 2x plus 1. Okay. Now if you enter 1 first or if you enter 2 first, it doesn't matter. It will give the same output. Okay. If you enter 1, it will give 3. If you enter 2, it will give 5. No matter how the order of 1 or 2 changes, it will just map it to that output. Okay, their order doesn't matter because here the policy is very strict. Similarly, here they are ensuring that the policy doesn't change as much, okay, on the basis or by the permutation invariant. Now to why they have implemented to ensure the robustness against changes in the number of the order of the visual satellite. So what happens? Suppose you have some receiver, okay. So receiver continuously, like it just changes things. It records various satellites, but it doesn't guarantee that it will capture the signal from all the satellites. So, so that to ensure the robustness, they have implemented a permutation invariant approach, in which if the number of satellites are not visible that much, like 3 or 4 satellites, then this could that could be robust. Our system could be robust against that scenario. It doesn't change the policy much. Common issues in GNSS, okay, while leveraging the NLS, which is non-line of sight and multipath indicators as a features to enhance position accuracy in a challenging situation and environment. So they are using the indicators as a features that could be used to correct for positioning accuracy. To validate performance of proposed framework, we compare positioning error with the state of art based like positioning method on two publicly available dataset. The result confirm that PC approach. Okay. Now they have to validate this. There is already employed some state of art model which is used for positioning for which are positioning methods. Okay, so they also predict the positions, but that positions could be corrected by our learning framework. So they are compared, like if they have used the state of art model, they get some accuracy, they get some error, but these errors should be minimal, not minimal. Then our learning framework and our PC DeepNet model will achieve much better results. Okay, so this is a very interesting paper. Now coming to the, okay, so here you could see that these are the satellites, and this is the non-line of sight vectors. Okay, this is a line of sight vectors because it directly reach to our receiver, which is mobile, and here's some signals getting blocked. Okay, so our deep learning model, what happens is, what it does here, it will first be processed, and it will execute some features, which are 7 features I could see: residual, Selvas vector, GDOP, elevation angle, and CYN node. So elevation angle, basically LOS vector have 3 components. So it is total 7 features, and these 7 features are fed in our model, which have encoder, aggregation, and decoder. Now these model will learn and predict the correction. Okay, and these correction will be added to the state of art based positions, estimated position, using RWLS algorithm, and that corrected position will further improve. So basically what it does, our model will learn the position error, okay, and it will just correct it. So that's a very amazing thing, that's very practical. So they have tested it out. As you can see, this is a train scenario, this is a train scenario, and this is a test scenario. Okay, so let's come to the results first, and in the later section, in the later video, I will explain the entire paper, what they have used. So they have used NAD coordinates. Okay, for scenario 1, they are referring that this is a very highly unlike scenario, like this is a very urban scenario, so here errors are more. This is a scenario 2, which is suburban, and this is a very favorable scenario. So these are the NED coordinates. Okay, so performance, evaluation of positioning error, these are the position errors. Okay, now what the result is, that 95% confidence interval refers that the estimated error is, we are sure that 95% of the time that the error is this. Okay, and now in scenario 1, the they have found these, like they have reduced to the 4 meters. That's very good thing. Okay, so here you can see that for scenario 1, in the north, with using WLS approach, we could plus minus 5.9, and they're 4.93 using common filters. They're 5.29, but our PC DeepNet got 2.95, which is very better than there. And in every north, east, down, the our PC DeepNet performs very good, very better than other. This is the architecture of the PIDNL model. In encoder section, they have used linear. So linear, they have 256 neurons as the input, and after that leaky ReLU, which will leaky ReLU. What it does is, it will just leaky ReLU means it will not vanish the negative, but it will just vanish negative by multiplying it. It will reduce its weightage. Okay, by multiplying with the decimal value like 0.1, 0.2. Okay, then linear 2, which have parameters of 2001, 12. Okay, and then this, and then linear 3, which have these number of parameters. Then dropout means they have not considered the weight of some neurons, because it is highly likely that our model will just overfit, and then they apply the recurring and then linear for the input. What is sum pooling? So sum pooling is like, it is a technique in which the the matrix column values are added. Okay, and they're pooled. Like I will show you some pooling. If you have heard about max pooling, then I think that might be very similar thing, right? This is sum pooling. I guess so. It is a sum pooling basically. It will sum up. Okay, that is a max pooling. Okay, as you can see, that in sum pooling they will sum. As you can see, 4 plus 1 is 5, right? And 5 and 6 plus 5 is 11. That is 16. That is sum pooling. Okay, there's sum pooling, and then similar for the decoder, leaky value, linear, and leaky value, dropout. In output, we get 33 parameters total. These number of parameters. So I guess okay. So they have also tested the same model with different number of parameters, and they have found that these number of parameters will have given best results. Okay, that's very amazing paper. I think we should definitely read it. Thank you.